on the other topics, I have many recordings in my YouTube channel that you can learn about polymer physics. But today I'm just going to focus on the fracture mechanics. And it's just a report to you. I learned, spending time learning in the last 2 years or so. I'm a newcomer, so thanks for coming. And certainly I have a lot to learn from you folks who are expert in the subject. So the subject is not new per se, meaning, in fact, presumably our knowledge and understanding of fracture of polymers is quite updated, well updated, with the books that are all quite recent. So let's see whether I have a different story for you. The first thing first, we learned that through those books that we need fracture mechanics to understand fracture behavior of polymers. So the burden to me is to explain to you folks why we need fracture mechanics, which amounts to having to understand what is the nature of fracture of polymers. More specifically, in fact, it means I need to explain why Griffith's scaling works. In other words, why your critical load, I should use just this, goes as this, which means why there is a constant Kc. And in fact, even more, what determines the magnitude of Kc. So, so this is why we need fracture mechanics, right? We were told that, you guys all do this, that the inherent strength of polymers is much higher than what we observe. So there must be defects. There must be something causing it to be weaker. And that's the standard way of doing it. It doesn't matter polymer or any other materials. If you want to know about the fracture strength of your polymer, well, you know it, presumably it's much weaker and there must be defects. So the way you go is you make a cut and learn about what is the toughness. And you insert that value into here, and now you can predict the strength of your material. By what? By having this defect size. But do we know the defect size? Is there a separate theory for it? No, we don't. In fact, the textbook goes in circles and says, gee, I don't know what is the defect size. Let me plug in G and I measure sigma B, then I get the defect size. So this logic is all circular. What I learned from my theory, polymer physics theory, on inherent strength of polymers, is the strength perhaps is only this much, not much higher. If that's the case, there's nothing to speak about in terms of fracture mechanics for the uncut. Don't get me wrong, when you have a big cut, you do want to invite fracture mechanics back to tell you how fracture occurs and crack propagates. So let me just sort of very quickly go through that. This is at least a field something like 60 to 70 years old for polymers. I know fracture mechanics is over 100 years, but these classical papers all talk about flaws. Okay, it's all flaws. And the next book says again flaws. Therefore, we need fracture mechanics. Flaws, Griffiths. So I just flash through that. So let me. There are a few who are not per se fracture mechanics people. So let me just remind ourselves how it gets started. I divide this fracture mechanics as I learned in the last couple of years of two pillars. You can call this one of the pillars started with English. And then the second pillar is, of course, due to Griffith's this energy argument that there's energy release rate. It's easy to calculate. And then this energy release rate reaches some level for window glass. Then basically, if I advance a little bit of the crack, release energy enough to pay for the energy to make the new surface, fracture is predicted to occur. On the other side, the pillar 2, of course, we have Westergaard's solution. We have stress divergence, and then Irving, of course, comes back says, oh, let's deal with that divergence by proposing there's plastic zone size. Note, this plastic zone size is suggested in the textbook to scale with k squared. But this is messy. You call it messy zone, damage zone, process zone, plastic zone. There are 4 names at least. It's just messy. So we tend to we tend to think this is a difficult problem. And lo and behold, luckily we have this fabulous relationship between K and G. So allow me to say, we can forget about pillar 2. Let's just do pillar 1, because they are all related. Instead of, I can simply compute for what is happening this way. So in other words, instead of having two pillars, the recent practice, I think as far as I can tell, please, I'm new, so please correct me if I'm anywhere wrong on this, is the recent tradition is basically taking this energy balance argument. It's certainly much easier to formulate a model, calculate energy, than to talk about stress. So in any case, we are basically back to this energy balance argument when you speak about the fracture criteria. So let me just move on. This is a powerful, important paper, 70 years now. This paper is the first one on elastomers. In other words, we learned about fracture mechanics, we started to apply to polymers 70 years ago. And they acknowledge, it's difficult. Where's the word? They acknowledge it's very difficult to, intractable, that's the word, to deal with what's happening at the tip because of the potentially stress divergence and the massive zone happening. So this paper explains, let's just go back to the energy balance argument story. Let's do it that way. It's much simpler. Not that he's not aware there's pillar 2. Maybe there's physics there to be learned. So, but the problem occurs right away in the 70 years old paper. That the fracture, the so-called fracture energy or so-called toughness or energy release rate is found for this polymer to be much larger than surface tension or surface fracture energy. So this makes this energy argument very difficult to persuade people that I still have, if it's much larger, why is much larger? Where the rest of energy go? Oh, that's the tradition. Where the rest of energy go? So let me just take you to my experiments, with my students. So we are going to take the challenge of Rivlin-Thomas and look at the tip. So we're going to look at what happens at the tip through birefringence is well established. So you can have an uncut, you can correlate the birefringence, which is just a way of reporting the strength field. In fact, molecular strength field, or the strength, basically deformation field, as a function of the amount of loading you have. So you can use that to calibrate and find out the correlation between them, and then apply that correlation to the tip. And so this will be the movie you see. If you use white light, it will be going through this Michael-Levy chart. So as light color changes preceding the thing, you have built more stress basically. And in principle, you can, I just fast forward a little bit, you can start to watch these different colors at the tip as well. Okay, so let's first start with plastics. You can work out the Westergaard solution. This is the solution in the form of the birefringence. So it will predict that away from the far field, the birefringence will just rise, singularly. And let's see what happens. So this is the experiment. This is the movie. You see the stress build up at the tip. It's kind of butterfly-like pattern. And then you can just analyze all the levels of stress and birefringence spatially, resolving it. And that's what you see next. So these are at different times of loading as you draw more. And this is close to where fracture occurs. You can analyze the RGB of this thing, and then you find what happens at the tip. Well, what happens at the tip is there's a point to see already. So I denote that stress, that principal stress difference revealed by birefringence as T, and I plot it as 1 over R minus 1/2. Therefore, approaching to the tip is going to the right. Lo and behold, well, rather actually surprising. So this is the Westergaard solution. It should continue forever, but it doesn't. It saturates that. The stress stopped growing saturate at a level, thanks to God, a level that you can resolve optically. So for this piece of plastic PMMA, it's about 100 microns. So it's trivial to resolve. And then, so since you have a plateau, I can confidently claim I have the stress at the tip. You see, if it's diverged, I couldn't resolve it. I wouldn't know what value that. I could resolve it now because the plateau. I plot this tip stress as function of load, the stress intensification factor. It's linear. Well, what does that mean? Well, since the relationship between them, by any scaling, is a length scale. So basically, this proportionality has the dimension of a new, shall I call it, characteristic length scale, P being a length scale. That's a typo again, that should be 1/2. This linearity marches on all the way to the point of fracture. In other words, this relationship not only works, it works at all load. In other words, the stress plateau actually occurs at all load as well. So all the way to the point of fracture. At the point of fracture, of course, your tip stress, in my view, can be regarded as reaching the point of inherent strength. So you have basically the story of the Kc being the inherent strength times P to the 1/2, right? Which is just this expression extended to the point of failure. So in this terminology, we will be able to understand the 60 years old data. We can even understand the spread. The spread means there is a change of a factor of 3 in C, which potentially comes from the fact that P can change. So in any case, I need to move really on fast. We're just saying that the other polymers does something similar. They all give me a plateau, stress plateau. So in fact, today's talk, I actually would like to focus more on the case of rubber. So let's move on from that and talk about rubber. So I may run out of time, so let me just try to indicate that I'm going to talk about something phenomenological about rubber. And there are really 3 topics here. Either as a function of the cut size, the nature of fracture in pure shear, and thickness dependence of toughness. So let's see how far I can go. But basically, this is the same technique. Because this sample we have a lot of birefringence, it's better to use white light so that you don't avoid this color saturation. So this thing just turns one color to black and white. In this case, it's a sodium light. So, and the stress at the tip start to build, and you have a microscope that you can resolve the pattern in that tip. And the lovely thing is the results are similar to the case of plastics. So you can resolve these patterns, you can read the intensity of the white and black, and you can see the oscillation of that corresponding to the buildup of stress coming from the side. As you count the number of fringes, your stress build up more and more. And this is reflected in this figure. So if you plot that local strength field as you approach to the tip, at different load, they all start to saturate instead of diverging. Saturate with a characteristic length scale, once again, 50 microns, easy to resolve. Okay, so through the birefringence, you could be able to claim again what is at the tip stress versus the load. And again, it's linear, with the slope revealing the characteristic length scale, which is correlated with the origin of this length scale is the existence of the stress saturation. For us, this is a new length scale because I will show you data. This scale is largely K independent, load independent. Therefore, it has nothing in common with the classical textbook plastic zone size, which should scale quadratically with K. So let me, since we have the example of plastics, the example of elastomers, let me summarize what I learned. This is just my report of my learning of the last 2 years on fracture mechanics. It's a very steep learning curve for me because I'm old. I'm just joking with you. So this is the classical linear elastic. Well, I think very much the samples we're treating are in the linear elastic limit. Okay. I complain like no tomorrow when I learn this. You got K, you got G, you got KC, you got GC. They are just operational definitions. It gave me no sense of how I can think differently about its meaning or it's about amplitude. But in any case, right, we know this, that they are constant. This is the amazing thing fracture mechanics established. They are constant. They are material specific. Okay? And then if you manage to have them, then in principle you can predict the fracture strength, except not really, because you really don't know what is your flaw size. In our case of polymers. In fact, if you flip that logic around, you find the flaw size is 1 millimeter. I don't see anything 1 millimeter in my sample at all. Okay? So, moreover, this framework of energy balance approach urges us to develop a model to calculate GC, such as Rivlin-Thomas tried. But of course, that's not clear whether this is a molecularly calculatable parameter in many cases. Okay. In fact, we already know it's not, because our stress plateau involves a scale much larger than molecular scales. So there's still a lot of mystery here. But let's see what was a different scenario I learned. What I learned is I'm now able to understand why it is a constant. A fracture mechanic cannot tell you because it's much larger than gamma, the surface vector energy. So there's no chance for you to argue why it is a constant. We know it is a constant by observation, but we don't know in theory why it is a constant. I may be wrong. Again, please correct me. But now I know. The Kc is determined by the inherent strength and this characteristic length scale, both of which are material specific. So I know it's a constant. Well, famous formula, I even know GC is a constant. It's involving a fracture energy density, or you call it, whatever you call the stress under curve, and P. And that fracture energy, of course, is involving the inherent strength again. So not only we know why it's constant, we actually know its magnitude is determined by these two parameters. Briefly speaking, you may want to increase this by not only increasing the inherent strength, but by somehow magically manipulating P. So in any case, this scenario urges me to do something different. I need to develop a model to calculate what is inherent strength, right, instead of GC. So, which is something we have done. But the mystery now is still what determines this characteristic landscape. We don't know. And that's why, oops, what happened? That's why we're pursuing this skill. So summarizing differently, you have an uncut, you get a fracture strength, and we blame that's coming from defect, and then you go to a pre-cut, and then you can, in principle, get a GC from the pre-cut inserted there. But if you look at the second pillar, it's a mess because we really don't know too much about how to speak about it. And in fact, look at the features of the description, right? It rises and with a constant cutoff. Our scenario that at least for polymers, it seems like that point is the inherent strength of an uncut sample, the fracture strength. Flaw is perhaps largely irrelevant. In other words, your polymer perhaps is flaw tolerant instead of flaw intolerant to the zeroth order. And look at this. It's utterly different. This is an experiment we found for polymers. All of it, meaning plastic and elastomers. not only there is the emergence of a stress plateau, but actually this plateau occurs even at low load. Not only there is this plateau, but this plateau has nothing to do with yielding and plasticity. It perhaps has to do with what you know, that the tip is blunted. In other words, when you make a cut going to experiment to do GC, you make a pre-cut. It turns out that pre-cut, your scissors, your blade doing it, the material just naturally respond to the thing and give you a cut. And that determines this value and can vary slightly. So the lucky thing is we were able to resolve. Our resolution is here. Sorry, our resolution is here. Therefore, we can resolve this plateau. Imagine if our resolution is only here, we'll be seeing the same thing. You see, right? If I cannot resolve this, if my resolution is here, I'll be reading a feature that's just the tip stress keep building, just like this says, beyond, if you cannot resolve this part. So I think we got lucky. This polymer involves length scales that's just managed, that's just amenable to our observation. I know we are a few minutes late, but still I want to keep it back in time. We start 10 more minutes at least, correct? Yeah. We started. My part is starting a few minutes late, but still, not then comfortable. I have plenty of things I can see. So this was standard fracture mechanics, right? We're just going to show that GC or KC is material specific, independent of cut size and geometry. So, for example, this is just a different way of plotting it, because instead of putting 1 over r, I had the cut size there, so that's why the plateau showing at different places. So you spread them out, a very nice way of doing it, I think. And you can also collapse them by plotting this way and normalizing your stress with K, and you get a sort of a master curve indicating a common place of plateauing of your stress. Okay, a common place. Moreover, this group of data involving very many different Ks, you see that zone size doesn't change with K, okay, instead of K squared. And you can, of course, even examine them at different Ks and see what look like at the tip. And the rest is all same story again. Here comes a 60 micron pops out, which is 3 times of this size. So they are correlated in some numerical way, simply. Instead of 20 microns, 60 microns, because there's a numerical factor between them. Moreover, by the time you K is reached, you get a common KC at fracture. Okay, so that's the first story. The second story is the most amusing. I really can relax and do have time to entertain you on this. This is that almost 70 years old paper. It's very clever. They learned that there is this energy balance argument, okay? So they are very inspired. Remember, I even showed you, they said, gee, the tip is too tough to do. I don't know how to think about the tip stress. So let me go back to Griffiths. And when I learned this, it just drive me completely crazy. And let me explain. Because this formulation and protocol, I call it, the Rivlin-Thomas protocol, as if it's a beautiful proof that the fracture problem is an energy balance problem. Let me explain. He do so-called pure shear. That means the sample is very wide, very short. And there is an argument I'm not going through to save your time. At the end of the day, beautifully, he elegantly argued that the GC, the toughness, is going to be a product of the height of your sample and the energy density of your sample at fracture. Okay? Now, think, please. In fact, let me put the next one. And this is found, watch that? This is found to be, this is found to be a constant, okay? It's a constant, independent of the height. It drove me completely crazy. I tell you, it says if you have a taller sample, I only need to store a little bit of density to get the same energy. Yeah, you get it? Because this side is constant. So as if it beautifully shows that this is the energy argument works beautifully. A bigger sample, I only need to store a smaller amount of energy density because that's enough, because my sample is bigger in volume. And that, of course, is against my insight about what fraction mechanics is. So even before student came to board, I did one lab experiment myself and got pretty clear. Yeah. So in any case, it turns out the story is very different. That's the most amusing thing. So we do this, okay? And you find it that at a higher height it breaks at a lower strand, blah blah blah, and you find the GC down this way indeed somewhat constant. But there's a big but. It turns out, by the way, this information was just not available 70 years ago to Thomas. They think it's too hard. But it turns out what? It turns out when you have a common load of a different height of your sample, remember the pure shear, the tip stress buildup is very different. In fact, this scaling was mentioned in some review papers. Oh, who doesn't know that? Meaning the K scales with sigma and the length scale square root. The cut size is no longer in the picture. The only length scale is the height now. And moreover, when it fractures at the common tip stress level. The rest is all, yeah. So at the end of the day, this scaling, I don't even call this a new scaling, but this scaling is replacing the cut size with the height of the sample in pure shear case can be used to completely demonstrate why the Rivlin-Thomas scenario follows. But in my opinion, it's a stress argument. So I think with that, I can close. And this is just another textbook story we're looking at. We learned that this Kc is thickness dependent, so we prepared several different thickness and proceeded. I'm going to cut it short. And then it turns out, depending on thick or thin sample, the place where stress plateaus occurs at different places. And so it turns out that there is a way to, and in our rubber case, it turns out this Kc is constant, independent of thickness. And so, in fact, this is a big story, right? You guys, I learned there is such thing as plane strain versus plane stress. So indeed, the thickness changing depending on the thickness changing depending on the original thickness as load changes. But there's some peculiarity about the fact it turns out that if you use the tip stress, they actually collapses. So I'm undecided about whether this thing teaches me that there is no change between plane strain or plane stress. I have a lot to ask you guys to learn from you guys. So this is the end. I'm a newcomer, so I hardly know anything, and I'm just had so much tough time about the fact this Kc and Gc is all operationally defined. So you give me no handle on what they are. It's just operational definitions from what I learned. Now, through the so-called pillar tool, looking into the tip in the case of polymers, we're able to resolve it. We know what it is. We know what it is away from a fracture and all the way to the point of fracture. And it seems to me K reaching Kc, G reaching Gc, you see, you can just translate everything. It's just a matter of the stress at the tip reaching inherent stress. So with that, I close. And the tip P is the meaning of P is the saturation of the stress. Thank you.